Hello students. Welcome to Smart Tricks for Study channel. In this video we will study about units and measurement. I am super excited to start this journey with you all, so stick around for some amazing content. If you enjoy what you see, don't forget to like, share, and hit that subscribe button to stay updated. Let's get started. Units and measurement. Let us look at the content that we will study in this video. Introduction. Classification of physical quantity. Units and its types. Systems of units. SI prefixes. Standards of length, mass and time. Errors in measurement and its types. Significant figures and rules. Rounding off the uncertain digits. Dimensions of physical quantities. Applications and limitations of dimensional analysis. Let us start with introduction. Physical quantity. In simple words, the physical quantity is any quantity that can be measured. Or all those quantity which can be measured directly or indirectly in terms of which the laws of physics can be expressed. Examples: length, mass, time, force, etc. A physical quantity can be classified into 1. Fundamental quantity. Quantities that cannot be expressed in terms of other quantities are known as fundamental quantities. For examples: mass, length, time, etc. 2. Derived quantity. Quantities which are derived from fundamental quantities are known as derived quantities. For examples: force, velocity, area, volume, etc. Note: 1. Scalar quantity means which have only magnitude, no direction. For examples: length, time, work, energy, etc. 2. Vector quantity means which have magnitude as well as direction. For examples: displacement, velocity, acceleration, force, etc. Next is units. Measurement of any physical quantity involves comparison with a certain basic, arbitrarily chosen, internationally accepted reference standard called unit. Types of units. Fundamental units. Units which are independent of other units and are used to define all other units. For examples: meter, second, kilogram, Kelvin, mole, ampere and candela. 2. Derived units. Units which are derived from the fundamental or base units. For examples: area, volume, velocity, force, etc. Now look at systems of units. A complete set of the fundamental units and derived units is known as the system of units. Here mainly 4 types of system of units are there. They are: 1. CGS system. Means centimeter, gram and second. 2. MKS system. Means meter, kilogram and second. 3. FPS system. Means foot, pound and second. 4. SI system. Means system international or international system of units. In this table we can know the system of units on basis of length, mass and time. For CGS system, Here length is measured in centimeter, mass is measured in gram and time is measured in second. Similarly, for MKS system, length is in meter, mass is in kilogram and time is in second. For FPS system, length is in foot, mass is in pound and time is in second. SI system. In SI system here are 7 fundamental or base units and 2 supplementary units. Base units. Let's see the base quantity, SI unit name and symbols. Length. SI unit name is meter with symbol small m. Mass. SI unit name is kilogram with symbol kg. Time. SI unit name is second with symbol s. Electric current SI unit name is ampere with symbol capital A. Temperature. SI unit name is Kelvin with symbol K. Amount of substance SI unit name is mole with symbol mol. Luminous intensity. SI unit name is candela with symbol CD. Supplementary quantity. There are 2 supplementary quantity. 1. Plane angle. SI unit name is radian with symbol RAD. 2. Solid angle. SI unit name is steradian with symbol SR. Now start with some units retained for general use. Name symbol SI unit values. Minute is represent with min and SI is 60 seconds. Similarly, R with H value is 60 minutes equal to 3600 seconds. Day with D equals to 24 hours equal to 86,400 seconds. Year with Y is equal to 365.25 days is equal to 3.156 into 10 to the power 7 seconds. Degree 1 degree is equal to pi by 180 radian. Liter L is equal to 1 dm cube is equal to 10 to the power minus 3 meter cube. Ton T is equal to 10 to the power 3 kg. Carat C is equal to 200 milligrams. Curie Ci is equal to 3.7 into 10 to the power 10 seconds. Quintil Q is equal to 100 kilograms. Barn B is equal to 100 femtometer square is equal to 10 to the power minus 28 meter square. Hector HA is equal to 1 square hectometer, that is 1 hm square is equal to 10 power 4 meter square. Atmospheric pressure. ATM is equal to 1.013 times 10 to the power 7 Pascal. SI prefixes. When the magnitude of physical quantity are very large or very small, it is convenient to express in terms of prefixes. EXA 10 to the power 18. Peta 10 to the power 15. Tera 10 to the power 12. Giga 10 to the power 9. Mega 10 to the power 6. Kilo 10 to the power 3. Hector 10 to the power 2. Deca 10 to the power 1. Deci 10 to the power minus 1. Centi 10 to the power minus 2. Milli 10 to the power minus 3. Micro 10 to the power minus 6. Nano 10 to the power minus 9. Pico 10 to the power minus 12. Femto 10 to the power minus 15. Atto 10 to the power minus 18. Standards of length, mass and time. Length. Standard meter is defined in terms of wavelength of light and is called atomic standard of length. A meter scale is used for lengths from 10 to the power minus 3 meter to 10 to the power 2 meter. A vernier calipers is used for lengths to an accuracy of 10 to the power minus 4 meter. A screw gauge and a spherometer can be used to measure lengths as less as to 10 to the power minus 5 meter. Measurement of large distances, parallax method. A method to measure distances to faraway objects. The apparent shift in the position of an object when viewed from two different positions is known as parallax. The distance between the 2 points of observation is called the basis. The star is viewed from two different positions from Earth, and the angle is measured by using the equation angle is equal to arc by radius. That is, theta is equal to b by d. D is equal to b by theta. Estimation of very small distances to measure the size of a molecule. Special methods like thin film techniques are used. Here, Fermi F is equal to 10 to the power minus 15 meter. Angstrom A is equal to 10 to the power minus 10 meter. Astronomical unit AU is equal to 1.496 into 10 to the power 11 meter. Light year LY is equal to 9.46 into 10 to the power 15 meter. Parsec Parsec is equal to 3.08 into 10 to the power 16 meters. Astronomical unit average distance of the Sun from Earth. Light year distance that light travels with velocity of 3 into 10 to the power 8 meters per second in 1 year. Parsec distance at which average radius of Earth's orbit subtends an angle of 1 arcsecond. Measurement of mass. The unit used to measure mass of atoms or molecules is Unified Atomic Mass Unit, U. 1 U is equal to 1.66 into 10 to the power minus 27 kilograms. Large masses in the universe like planets, stars, etc., can be measured by using gravitational method. For measurement of small masses of atomic, subatomic particles, etc., we make use of mass spectrograph. Measurement of time. To measure any time interval, we need a clock. The cesium atomic clocks are very accurate. Accuracy and precision of a measurement. Accuracy of a measurement is a measure of how close the measured value is to the true value of the quantity. Precision is the resolution or limit with which the quantity is measured. The accuracy may depend on the limit or resolution of the measuring instrument. Errors in measurement. Error is the uncertainty in a measurement. It is the difference between measured value and true value of the quantity. Types of errors. 1. Systematic errors. 2. Random errors. 3. Least count errors. Systematic errors. The systematic errors are those errors that tend to be in one direction, either positive or negative. The sources of systematic errors are instrumental errors. Arise from the errors due to imperfect design. Calibration of the measuring instrument. Zero error in the instrument, etc. Imperfection in experimental technique. 2. Personal errors. Arise due to an individual's bias. Lack of proper setting of the apparatus or individual's carelessness in taking observations without observing proper precautions. Parallax error, etc. 2. Random errors. This error occurs irregularly and is random with respect to sign and size. Arise due to random and unpredictable fluctuations in experimental conditions. Random errors can be minimized by repeating the observations several times. 3. Least count errors. Least count is the smallest value that can be measured by an instrument. Least count error is the error associated with the resolution of the instrument. Least count errors can be minimized by 1. Using instruments of higher precision. 2. Improving experimental techniques. Significant figures. The number of digits in a measurement about which we are certain and one additional digit which is Uncertain is known as significant figures. The number of significant figures indicates the accuracy with which the quantity is measured. Rules for determining significant figures. All non-zero digits are significant. Example, 42.3 has 3 significant figures. 1234 has 4 significant figures. 2. All the zeros between two non-zero digits are significant, no matter where the decimal point is, if at all. Example, 4.03 has 3 significant figures. 1204 has 4 significant figures. 3. If the number is less than 1, the zeros on the right of decimal point but to the left of the first non-zero digit are not significant. Example, in 0.00 to 308, the underlined zeros are not significant. That is 2308 has 4 significant figures. 4. Trailing zeros in a number without a decimal point are not significant. Example, 1,53,000 has 3 significant figures. That is 15,300 is equal to 1,53,000 is equal to 153. 5. The trailing zeros in a number with a decimal point are significant. Example, 3.700 has 4 significant figures. Rounding off the uncertain digits. While rounding off measurements, we use the following rules by convention. If the digit to be dropped is less than 5, then the preceding digit is left unchanged. Example, x is equal to 6.53 is rounded off to 6.5, and x is equal to 8.64 is rounded off to 8.6. 2. If the digit to be dropped is more than 5, then the preceding digit is raised by 1. Example, x is equal to 6.56 is rounded off to 6.6, and x is equal to 14.758 is rounded off to 14.76. 3. If the digit to be dropped is 5 followed by digits other than 0, then the preceding digit is raised by 1. Example, x is equal to 16.351 is rounded off to 16.4, and x is equal to 6.758 is rounded off to 6.8. 4. If digit to be dropped is 5 or 5 followed by zeros, then preceding digit is left unchanged if it is even. Example, x is equal to 5.250 becomes 5.2 on rounding off, and x is equal to 11.650 becomes 11.6. 5. If digit to be dropped is 5 or 5 followed by zeros, then the preceding digit is raised by 1 if it is odd. Example, x is equal to 6.750 is rounded off to 6.8, and x is equal to 19.150 is rounded off to 19.2. Dimensions of physical quantities. Dimensions are like building blocks for measurements. All the physical quantities represented by derived units can be expressed in terms of some combination of 7 fundamental or base quantities. The dimensions of a physical quantity are the powers, or exponents, to which the base quantities are raised to represent that quantity. Basic building blocks, we have 7 fundamental dimensions. 1. Length has the dimension L. 2. Mass M. 3. Time T. 4. Electric current A. 5. Thermodynamic temperature K. 6. Luminous intensity CD. 7. Amount of substance mol. In mechanics, all the physical quantities can be written in terms of the dimensions L, M, and T. Example, for example, the volume occupied by an object is expressed as the product of length, breadth and height. That is V is equal to L into L into L is equal to L cube. Similarly, for physical quantity force. Force is equal to mass into acceleration is equal to mass into length divided by time square is equal to m L by t square. That is equal to mLT to the power minus 2. Dimensional equations of V, volume, small v speed, F, force and ρ, mass density may be expressed as given below. In this table we study more physical quantities, relation with physical quantities, dimensional formula, SI units. Just go through it. Last part: applications and limitations of dimensional analysis. Applications of dimensional analysis. A. To check the dimensional consistency of equations. B. To deduce relation among physical quantities. Limitations of dimensional analysis. The dimensional consistency does not guarantee correct equations. The arguments of special functions, such as the trigonometric, logarithmic and exponential functions, are dimensionless. A pure number, ratio of similar physical quantities, such as angle as the ratio, length by length, refractive index as the ratio, speed of light in vacuum by speed of light in medium, etc., has no dimensions. Dimensionless constants cannot be obtained by this method. It does not distinguish between the physical quantities having same dimensions. This completes units and measurement chapter. If you enjoy what you see, don't forget to like, share, and hit that subscribe button to stay updated. Now let's see some MCQ based on this chapter. Let's get started. 1. The units that are used for fundamental physical quantities are called: A. System of units. B. Fundamental units. C. Derived units. D. All of these. Answer: B. Fundamental units. 2. The SI unit of electric current is: A. Watt. B. Joule. C. Volt. D. Ampere. Answer: D. Ampere. 3. The SI unit of frequency is: A. Meter per second. B. Radian per second. C. Newton meter. D. Hertz. Answer: D. Hertz. 4. The SI unit of solid angle is: A. Radian. B. Degree. C. Steradian. D. Radian per meter. Answer: C. Steradian. 5. Which of the following physical quantity is not a fundamental quantity? A. Length. B. Temperature. C. Electric current. D. Energy. Answer: D. Energy. 6. Young's modulus of a material has the same units as: A. Pressure. B. Compressibility. C. Strain. D. Force. Answer: A. Pressure. Because Y is equal to stress by strain is equal to force by area divided by dimensionless. That is, Y is equal to pressure. 7. Which of the following physical quantity has same unit in CGS, FPS, MKS and SI systems of unit? A. Mass. B. Length. C. Time. D. Energy. Answer: C. Time. 8. Light year is a unit of: A. Time. B. Distance. C. Mass. D. Energy. Answer: B. Distance. That is, light year is a distance which light travels in 1 year. 9. SI unit of pressure is A. Pascal, B. cm of Hg, C. Dynes per cm square, D. Atmosphere. Answer: A. Pascal. The SI unit of pressure is Pascal, represented as PA, which is equal to 1 Newton per square meter or kg per meter per square second. Interestingly, this name was given in 1971. Before that, pressure in SI was measured in newtons per square meter. 10. 1 nanometer is equal to A. 10 to the power 9 millimeter, B. 10 to the power minus 7 centimeter, C. 10 to the power minus 6 centimeter, D. 10 to the power minus 9 centimeter. Answer: B. 10 to the power minus 7 centimeter. 1 nanometer is equal to 10 to the power minus 9 meter is equal to 10 to the power minus 7 centimeter. 11. Joule second is the unit of A. Work, B. Pressure, C. Momentum, D. Angular momentum. Answer: D. Angular momentum. The unit of angular momentum is joule second. 12. Unit of power is A. Kilowatt, B. Dyne, C. Kilowatt hour, D. Joule. Answer: A. Kilowatt. 13. The unit of angular acceleration in the SI system is A. Newton per kg, B. Radian per square second, C. Meter per square second, D. Meter per kg Kelvin. Answer: B. Radian per square second. Angular acceleration is equal to angular velocity divided by time is equal to radian per square second. 14. A micron is related to centimeter as A. 10 to the power minus 8 centimeter, B. 10 to the power minus 5 centimeter, C. 10 to the power minus 6 centimeter, D. 10 to the power minus 4 centimeter. Answer: D. 10 to the power minus 4 centimeter. 1 micron is equal to 10 to the power minus 6 meter is equal to 10 to the power minus 4 centimeter. 15. Parsec is a unit of A. Distance, B. Time, C. Velocity, D. Angle. Answer: A. Distance. Parsec is astronomical unit of distance. Don't forget to subscribe the channel for more videos.